Hello students, this is lecture number 22 and we are going to start a new chapter, chapter number 6, and this is about now finite element analysis of what is known as a scalar value problem. Scalar value problem but multidimensional. Yeah, so scalar value problem multidimensional. So to be specific, we will start, actually we will work on 2D, and if you know how to work with 2D, you can automatically work with 3D as well. You can extend it too, but we will study here 2D only. So let's understand what is the meaning of that. So far we looked at 1D problem, and we have 1D problem, and we had we looked at problems where there was a displacement, right. So you at nodes you had a displacement, but displacement is a displacement is a vector actually, right. However, same equation we also used for T, heat transfer problem, right. Temperature T, this is a scalar. Okay. Now, since we had only one dimension, so we use the same equation to denote both. Which one? The elasticity problem and heat transfer problem. Okay. Now, if we have 2D problem, then we will see that equation will change, it will not be the same. In 1D, both the equation elasticity, 1D elasticity problem and 1D heat transfer problem looked the same, differential equation was same. But as we move to 2D, we will see that elasticity problem will be different and heat transfer will be different. Why? This is because this is heat transfer problem is it has a scalar variable. So, it has temperature as variable, temperature T as variable, which is a scalar value. On the other hand, elasticity had a displacement, right, displacement u, which is a vector, and this will be a vector, this will be a vector value problem. Okay, what is the meaning? We will know later on more, but let us start with 2D heat transfer problem. Okay, and let us say you have to solve something like this one. Yeah, and why shape like this? We can have any shape, we can have a shape like this. This is 2D. Yeah, and this is domain, right. So, omega equal domain, and then there are boundaries. So, on boundaries you will have either essential boundary condition. So, you can have from here to here, let us call it gamma 1, and from here to here let us call gamma 2. What is the difference? Difference is, let us say at gamma 1 may be for essential boundary condition, that is some temperature will be given. Yeah. So, basically T is given, maybe T equal to T naught, yeah, example, and gamma 2 is another boundary where natural boundary condition will be defined. So, either the slope is given, means there will be something given there, and that will be in terms of derivative basically. So, but what kind of derivative? Well, we will see. So, basically what is given is flux, right. So, you know that Q will be given. Yeah. So, Q now we wrote as a vector here Q. Yeah. So, Q is given because flux is a vector, although temperature is a scalar, because the flux has a direction. Yeah. So, it goes, this is defined as the how much heat is flowing per unit area and per unit time. So, area itself, you will see that area itself is a sense of direction it has, right. So, for example, here if you say if the heat is flowing outside the boundary. So, if you see here it is this direction, here it is this direction, here this direction, here this direction, and so on. Yeah. Okay. Now, let us look at just one element out of it, very a small, you know, control area that we are getting out of it. So, this is something like this we have, yeah, and this we are going to analyze how. So, here this may have some coordinate system, this has x and y. Similarly, we will have this under some coordinate system x and y. Okay. So, let us write on a fresh page so that we can write it the values of several things here. So, one thing is this may have some source, heat source, yeah, where heat source S will be in watts per meter square. Yeah. Okay. Because this is area, so heat per unit time per unit area. Yeah. So, this kind of unit it will have. So, this a small element will also have some S, same value of S, watts per meter square. So, we have some S here. Then from here to here, let us assume this is dx. Okay, from here to here, let us say this is dy. Okay. Now, temperature, maybe we can say this is T here, okay, and here the temperature could be T plus dt del T over del x, okay, and multiplied by dx. Okay. Similarly, we can have, so basically we can have this T here. So, if T is here, we are going to write like this one, or you can have T here, accordingly this we can also write in minus delta T like this one. Yeah. Okay. So, similarly we can have here will be T plus del T over del y dy. Okay. Okay. So idea is, if we have t here, then this is how it is moving. So you have at this, if this end t, you have at this end t plus del t over del x dx. Similarly, if this end we have t, this end we have t, then also this end we have t plus del t over del y dy. Okay. Okay. Now we can take t both the sides, because finally we have this depends on we are going to take values from in both the directions separately. Yeah, so we will see the equation, how it is coming like that. Okay, so the idea is it depends on the distance. So we can also have we can write like a t1, so t1 here, then t1 plus dt over dx this, then we have t2, then t2, we can also write like that also. So okay, maybe we write like this only. So let's say we equate t1 here means phase number 1, so t1, and this is what the variation of t b3 x. So here we don't need to do t1, because this is talking about the actual temperature, how it is changing. Yeah, so similarly here also we can say this is t2 at this phase, and this is how t2, and then how the how the temperature is changing with respect to this is a gradient of temperature. Basically this is what it is talking about, and multiplied by dx, that's what it gives, right? So yeah, now what we want to see here is how the energy, how the energy is conserved. Yeah, so energy is conserved. So the temperature, we are talking about the temperature here. However, we should be concerned about how the flow is actually. Yeah, so basically this is one thing. From here we can get, so actually we have to look at how the q is flowing. So if it is qx here, let us say this is a q, this we will make use of, but before that, so that we can use the heat coming and going, we have to define the flux. So we have qx which is coming here, and going out is qx plus del qx over del x times dx, and in upward direction we will have qy, and going up will be qy plus del q, right, sorry, qy, so del q y over del y dy. Yeah, and then we have s. Say this is figure number 1, this is figure number 2. So the area, we know that from here to here is dx, and from here to here is dy. So from figure 2, what do we get? We get conservation of heat, basically energy we are talking about, and the values, whatever this is, this one is qx. Okay, so we will have the qx and qy. So we write here qx qy, this will have watts per meter square. Yeah. So we will have the or watts per meter, because this is two dimensional basically. So this is 2D. So we can assume either thickness equal to 1, or we have just this will be watt per meter type of units. Yeah, because this we have like this. Either we can have watts per meter square, and then you take thickness here as 1, so that area becomes 1 multiplied by distance from here to here, or you can assume qx qy is in terms of watt per meter only. Okay. So if that is the case, we have the energy coming to the system is qx and qy. So we have qx plus qy, which is coming to the system, plus, okay, we also have to multiply. So let us multiply qx multiplied by dy. Okay, then let us make it watt per meter square only, so that we can multiply by 1. We assume the thickness is 1 only, and then we q y dx into 1 plus s dx times dy. So these are the heat which is coming to the system, and this much are going out. So this has to be equal to qx plus del q x over d x dx, okay, times dy plus qy plus del qy over del y dy times dx. Okay. Okay, or you can see that here, oh yeah, here you have multiplied by 1, here also, here multiplied by 1. So what do we get here? So qx times dy will get cancelled, and qy times dx, qy times dx will get cancelled. So we will have only s equal to qx over del qs over del x and del qy over del y only. So if you simplify, what we get is simply del qx over del x plus del qy over del y, okay, is equal to s. So this is what the equation is. Okay. So this is the equation, or we can write also in terms of assume that q, which is a vector, you can assume will be qx I plus qy z. So then you have divergence, which will be, okay, so that's a, they call divergence, will be equal to del qx over del x plus del qy over del y. Okay, so where this means del over del x I plus del over del y j, that's what it means. Okay. Okay. So, looking at this one, since this is equal to this and divergence of q it becomes like this, and hence we have this is equal to S, or simply divergence of q minus S equal to 0. So, this is the equation basically. Yeah. So, this is the what the strong formulation is. Where now you can write further what is the meaning of q here, but q we know that q is qx I plus qij, this is a vector, and so this is, we call it divergence of q minus S equal to 0. Okay. Now, how is the q defined? What is the meaning of q? Yeah, so for that we have to look at here. Yeah, so we q, you know that this one is we know the Fourier. Yeah, this is the Fourier law, Fourier rule for this so we know that in 1D you have q equal to, we call it minus k dt over dx, right. This is how we did. So, in 1D basically what it means is this equal to I, you can write like this. Yeah. So, I y, because this is there is only x direction, so we are writing like this one. In 2D we will write q is equal to, now here we will have little bit difference here. So, we cannot write exactly like k like this one. Okay. So, we will have like dt over dx, but this will have we have the two directions like you can see here, right. So, the q will be flowing this way and this way as well. So, we can find out from here. So, in this direction, so there is a difference, and because of that temperature difference, because of that the heat will flow. There may be some difference between here and here also, because of that also that there will be some flow going on like this one, right. So, because of from this side to this side also will go, and from this side, so this side also it will go. So, it should depend on temperature gradient of both the sides, it is not just one side. Okay. So, what is the meaning of that? Okay. So, in order to derive in 2D, we can also write in terms of like matrix formulation, and then we will understand what is the meaning of that. So, basically here when you say q you can also write as a matrix formulation, and you can call it qx qy like this. Okay. So, this is matrix formulation. So, you say matrix. Yeah. Okay. Okay. Now, for that probably we can, instead of saying like this, we can write maybe as qm, saying that this is a matrix. Yeah. So, bar with no bar probably, yeah. So no bar like this one, no arrow here. Okay, so this we have, so this is the qx and qy. Okay, now this qm, so I write here first. So this qm, which is given by qx and qy, will be equal to, instead of having one k, we will have some different kind. So we will have minus here, same as earlier, yeah, and then we have k11, k12, k21, k22, and then dt over dx, dt over dy. So this is what is the Fourier law in 2 dimension. Yeah. So basically this is equal to minus d, and then this one is temperature gradient basically. So minus d and then del t over del x and del t. Okay. So where d is equal to k11, k12, k21 and k22, which is a material property. So if it is isotropic material, then this will be k11 will be equal to some value k22, which is equal to k, and k12 equal to k21 will be equal to 0. So that is the meaning is that in that case the gradient of this will not be influencing the heat passing to this direction, meaning that if we have k0 0k as D matrix, then it will just depend on what is the temperature difference is, I mean temperature gradient in one direction. It will, what is the gradient in the other direction will not influence the heat flux in the other direction. If it is anisotropic, it is going to influence. Okay. So basically, if it is isotropic, then you can actually independently look at both the sides. So you can say independently, you can say if isotropic, say isotropic, then you can say this q will be nothing but this minus this divided by dx, right. So if it is isotropic, then you know that qx will be equal to nothing but this minus T1. So this becomes del T over del x divided by, so simply this will be change in T divided by change in x, and what you get minus minus k has to be there. So simply it will be minus k and change this minus this, which becomes this divided by dx. So you get simply this one. So what you get is minus k dt over dx. And similarly qy will be equal to minus k dt over dy, sorry, partial derivative. Okay. So, this is true only when this is isotropic. If this were an isotropic, then we will count the gradient, means the qx will depend on gradient in this direction plus gradient in the direction as well, and we will write, and that would be something like this equation. However, when it is isotropic material, then we have k1 1 equal to k22, which equal to k, and k21 is equal to k12 equal to 0. So, this and this will be equal to 0 when it is isotropic material. Okay, so far, we are clear about the equation, and we can write accordingly. The equation becomes equal to d. We can write as d. Let us say del t matrix. This is given by del t over del x, del t over del y. That's how we write. Okay. So, then our equation becomes D, which is a matrix, times del t, okay, and that becomes this is what we get here. See here, this one. So, we have minus d del t is equal to q is equal to q, right. So, we have, so we write, so far what we get, we call it qm, or let us call q tilde, something like that. Okay. So, not bar, but we will have a tilde, like something like this. Okay. So, we have q tilde is equal to d del t, okay. Minus will be like this one, okay. Now, if you look at earlier, we have another thing here. So, we wrote like this one. So, in that case, so if you look at this, del the qx and qy, this is in form of qx and qy. So, we have same form. Does it really means that okay. So, we say we write like this. So, this is del, either we can have like this one, then we call it like a del del over del x I plus del over del y j, or you can have this is vector form, or you can have matrix form where you still have del here, and we will have a tilde type thing. So, will be equal to we will have like this del over del x and del over del y. Okay. So, when you have arrow, this means this is a vector form, we have tilde here, this will be of matrix form, remember that. And hence, we have del, this q will be, so remember we put a tilde here. So, we have a D matrix multiplied by tilde, which is operating on T. So, T will being a scalar will go here and here automatically. So, we have like this. Okay. Now, the equation of equilibrium is equal to, if you see the, we have vector form, right, we call it this times q, right, is equal to s, yeah, or we can write minus s equal to 0. This is equation of equilibrium, but this is in vector form. We can also write the same thing in the matrix form, and how can we write? So, this one we can write it as, so we have del, can write as del tilde multiplied by q tilde minus s equal to 0. So, this will be a like a matrix form. How? Because if you see here, this will be t here like this. Okay. So, why? Because meaning of this will be, this is transpose. So, we will have like this, del over del x, del over del y multiplied by q, qx, qy minus s equal to 0. Yeah. Okay. So, we have that. Now, this itself, which is like this, is given like this one. Yeah. So, from here what we will get is del tilde transpose and then q is nothing but minus this. So, we have minus d del tilde t, right, minus s equal to 0. Okay. So, you can write the final one. This will be equal to, let us write final, that becomes del tilde transpose d del tilde t plus s equal to 0. Yeah. So, our equation of equilibrium, finally we can write equation of equilibrium or the strong form. You can write two way. One way will be the vector format, and what is that? We say del the divergence of q minus s equal to 0. Yeah, or you can have in write in matrix form, and this will be del tilde, yeah, and then you have transpose of that, then q tilde, right, minus s equal to 0. Or same thing, if you go ahead, we know q is equal to, for an isotropic we can write in general, this value will be del tilde transpose, then d del tilde and then temperature T plus S equal to 0. So, this is in general for anisotropic, yeah. For isotropic you will see D will be equal to K multiplied by 1001, which equal to K times identity matrix, and what you will see simply is del tilde t, then you will have simply del tilde T for transpose here. So, this is T for transpose, this is T for temperature, and you will have value K here and plus S equal to 0. So, you can write this way, yeah, or for isotropic also we can write isotropic D, yeah. You can also write this one, which will be easy, and y we can write del dot q, and q will be equal to minus k and gradient of t, right, minus s equal to 0, or simply we can write it here as divergence of k gradient of t plus s equal to 0. Yeah, so you can also write like this. Yeah, so remember, this is, in this case, this k is a constant, hence we can write like this one. So we have different forms, the same thing, it is talking about the same thing basically, but we are writing differently. Here we are writing in terms of matrix, here we are writing as a vector, here also we are writing as a vector, yes, matrix a tilde we are talking about, then we have the matrix system. Now the next thing is how to find out the you have to also give the boundary condition. So you know the equations are not sufficient by itself, you also have to give the boundary conditions. So what kind of boundary condition you can give? So as in the figure we have two kinds of boundaries. So you can see this gamma 1 and gamma 2, and I said gamma 1 where essential boundary condition is given. So that's temperature is defined. So T equal to T naught is, for example, the temperature given defined. This natural boundary condition Q naught has to be given on this one. And what is the meaning of that is you have to give some sort of, so for example, you may give that the value perpendicular to this, perpendicular to the boundary, right, and how you do, either you will write like this, right. So Q dot n is equal to Q bar, you can give like that, yeah. Okay, that really means that if you look at that, if n, you can also have something like this, Q as you know will have so let me write here. So Q will have Qxi plus Qyj, and then we have n which will be equal to nxi plus nyj. So from this Q dot n will give you nothing but this will be equal to Qx nx plus Qy ny, or you can write in terms equal to Q tilde, you can also write Q tilde transpose n tilde. Okay, so where Q tilde means we are writing vector Q in terms of a matrix notation, n also vector n, which is a unit vector perpendicular to the boundary, we are also writing at this. So where Q, so where Q tilde will be equal to Qx and Qy, and n tilde is equal to nx ny. Yeah. So this is the boundary condition. This is how the boundary condition will be given. Thus we see that we have the equation, the strong form ready. Now next thing is to how to, so the strong form is given by this, right? Either we can write like this one or we can have like this one. So we can actually take the easiest form like this one, and from this one you can find out what is the weak formulation. And we, okay, so why we did all those things? Okay, so we will use these two later on, but for simplicity we start with the vector formulation. We will see the basically how to apply the how to obtain the weak formulation. Okay, so let's start with the easiest strong formulation, and this is the equation. As you know, this will be del q over, sorry, not del, so you have divergence of q minus s equal to 0, and along with the boundary condition will be what, as I we saw earlier. So where it will be t given, t equal to t naught at 1, yeah, and then, or you call it gamma t, where t is given, and then q dot n equal to q naught at gamma 2 or gamma q. Okay. So these are the boundary conditions given. Now, so just look at this, and we have to this is what that is, the strong formulation, the strong form, and in order to find out the weak form, what do we call, what do you do? Weak form, we multiply by some w to this equation, right? So this and now this is we have to integrate over the whole domain. Say domain in this case will be any area we are talking about, right? So let us say plate which is of this shape, so the whole area will be its domain. So you have to integrate it, and that will be equal to 0. So or you can say or so this has to be on the whole domain. So or we write w and then divergence of q d omega minus ws d omega equal to 0. Okay. Okay, so now we have to find out this one. So this is the has to be evaluated over the whole domain. So we can say this is I1 minus 2 equal to 0. Yeah. So where this is this is 1, this is 2 we are talking about. So now let's evaluate this one. As we know, w is there, so we don't need to simplify, it's already simplified. Only we have to look at this one, what is the meaning of that. So this is w multiplied by this divergence of q, right? Okay, so in order to find out this one, we have to use the integration by parts. Okay, so what we will do is we are going to use divergence of w times q. So here q is also the vector, remember, and w is not. So q is vector. So we have to write like this: q is a vector, not to forget. Q is a vector, s is not, yeah, and w is also not a vector. So again, in a statement you have to say this is valid for any, this is true for any w with w is equal to with w equal to 0 at gamma t, where, so since t is defined t equal to t naught at gamma 1 gamma t, hence w will be 0 at gamma t. So, this will be applied as we know. Okay. Okay, so the I, let's the first one, if you this one, how we obtain this. So, instead we will use this, we will find out what is the meaning of that. So, what? Divergence of w times q. Okay. Okay, so if you look at this, we can have this equal to, right. So, what do we have? We will have del over del x I plus del over del y j, right, and then we have a dot, and then we have w, and then we have q, and we know that this means w qx I plus w qy z. Okay, that's what the meaning is. So, equal to what do we get? If you see, so first this goes to this, so we have a dot here, so only I and I will work and j will work. Okay, so simply we will get del over del x w qx plus del over del y w qy, okay, will be equal to, now we have differentiate both of them. So, we have to do like this, del w del x qx plus w del qx del x plus del w del y qy plus w del qy del y equal to, we write, and then we have qx qy. So, here we can have this and this together. So, we can write like this, del w over del x qx plus del w over del y qy, okay, plus we have this w can be in common, so plus w del qx del x plus del q y over del y. Okay. So, equal to, so what do we get? We get from here we can see that we get del, you can write like this, this is will be gradient of w dot q plus w times divergence of q. So, basically we get the equation of this, yeah. So, we can write that really means this. So, gradient of divergence of w times q will be equal to gradient of w multiplied by dot q plus W divergence of Q, like this. Okay, so why we did that? Because this is we will use integration by parts, and you can see here that in this case we have del W times divergence of Q. So, W times divergence of Q. So, this will be equal to this minus this. Yeah, so this is the takeaway from here. So, we can write on the next page. So, W divergence of Q. So, W times divergence of Q is equal to divergence of W times Q minus this gradient of W dot Q. So, gradient of W dot Q. Okay. So, this is what we get. Now, we can put this value to the this one. Yeah, so this integer 1 I is equal to like this, right. So, I of so basically I will be equal to this W times divergence of Q d omega will be equal to so we have divergence of WQ minus gradient of W dot Q d omega, okay, or is equal to divergence of WQ d omega minus omega gradient of W dot Q d omega. Okay. Okay, so we have this now. Now, next thing is we have to apply the divergence theorem. Okay, so divergence theorem. Now apply the divergence theorem. Okay, so what is divergence theorem? Divergence theorem says that basically in terms of this one, this really means that this divergence of WQ d omega, let us write not Q but any vector P, right, like this, or the divergence of a vector P d omega is given by n dot P in okay, so n dot P integrated over the whole boundary. Okay. So, basically this is what a divergence theorem is. So, what it does, from the integration over the whole domain, this equivalent to integration of this. So, what you did like this del is replaced by, this delta has been replaced by n, that is it. So this del dot, you have n dot here. Here you are integrating over the whole domain, over the whole area. Here it tells you no need to integrate over the whole area, just bound integrate over the boundary, that is it, and it is sufficient. Anyway, this like I will explain a bit more in the next video lecture, but if you do engineering mathematics, these divergence theorems are typically taught to you. So, you may be knowing already. So, right now I assume that you know the divergence theorem, although in the next lecture also we will see what is the physical meaning of that, what is the meaning of this exactly, so that you can remember it. Okay. Now, this so we can apply the same thing here. So, only thing is instead of P we have this. So, we have this is nothing but P, right, this is what the P is, and hence we can have I equal to, so we will have equation we can write like this n. So, we have n dot w q, where w is a vector, sorry, w is a scalar. So, w will come out. So, we get w times n dot q, or q dot n you can write also. Okay. So, w times q dot n. Okay. So, we get that really means we can write like this. So, we get I equal to gamma, then w q dot n d gamma, and minus integrated over the whole domain, and then gradient of w multiplied by q, okay, and d. Okay. So, that means our equation, the weak form, that means weak form we have that, and what is that? So, we will have this equation first, I and 1 minus 2, right. So, we have 1 this and this one. So, 1 we have here, right. So, so we can write this. So, w q times n, w q, okay. So, this is over the whole boundary, and then minus omega del w dot q. So, this will be like that, d omega. So, we have 1, and then we will have minus second part minus omega w s, yeah. So, d omega, and that is equal to 0. So, this is the whole thing which is the weak formulation, and now based on that we can go ahead from there. So, we have to now understand what is the meaning of that. So, typically q dot n is given, right. So, either you have w, either you have u given, u means t given, either you have t given. So, just see where you can write this one into two parts, right. So, we can write this as two parts. So, this w q dot n d gamma will be equal to, where temperature is given. So, this w q dot n d gamma plus where q is given, w q dot n d gamma, sorry, this will be gamma q. Now, we know that W will be 0 where temperature is given, right. So, this term will be equal to 0, yeah. So, we write this term equal to 0, yeah, and the other term, this one, where Q will be given, and Q will be given in terms of Q naught only, right. So, we have W times Q naught at those boundaries basically. So, finally, what will a value will be is integral over the boundary where Q is given or natural boundary condition is given of what W Q dot n d phi. Yeah. So, only this term will remain intact. Okay. So, basically we got the weak formulation. From there we can do the finite mid formulation, we can have the test function and so on, we can do that, but this is the weak form. For that we have to use the divergence theorem. So, we will look at in the next lecture video, we will look at the Green's theorem, yeah, and the divergence theorem, yeah. So, okay. So, that is all for this video lecture.